Welcome to The Explainer. Today we're doing something a little bit crazy. We're going to completely dismantle your intuitive, everyday understanding of reality. You know that feeling when things seem just a little too orderly? Like maybe there's a deeper, much stranger truth hiding right beneath the surface of everything we touch and see. Well, buckle up, because today we are taking a trip into a scientific wonderland. And the crazy part? It's not some far-off dimension. It's the very universe we live in. We're diving deep into Albert Einstein's special theory of relativity, and we're going to see exactly how it broke and then brilliantly rebuilt our entire concept of space and time.
Okay, so let's just jump right in with a question that honestly feels like a glitch in the matrix. It completely challenges the fabric of how we perceive the universe. What if a meter isn't always a meter? And what if a second isn't always a second? Think about it. Literally everything we build, everything we measure, it all relies on this rock-solid assumption that distance and time are absolute constants. But what if they aren't? What if they're actually flexible? To really grasp why this question is so earth-shattering, we kind of have to look back at how we used to think the universe worked. For centuries, we relied heavily on Newtonian mechanics. And honestly, it painted a picture of the universe that makes perfect sense to our everyday human brains. If you ask practically anyone today how space and time work, they're probably going to describe Newton's model without even realizing it. It is just that deeply ingrained in us. Newton gave us these beautiful, predictable rules that perfectly explained how apples fall, how planets orbit, and how everyday stuff moves around us. It felt complete, you know? It felt absolute. So the crucial takeaway here is that Newton basically saw space and time as a neutral, static backdrop. Think of it like a fixed, rigid stage where all the events of the universe just play out. In this classical view, space exists completely on its own, independent of whatever is inside it. If two objects are 1 meter apart, well, they are 1 meter apart for everyone, no matter what. And time is just this giant, universal clock ticking away at the exact same rate for everyone, everywhere. Sounds like pure common sense, right? Well, science was about to hit a massive roadblock. Now, what's genuinely fascinating is the sheer contrast between our gut intuition and actual physical reality. By the 1800s, we had Newton's laws for motion all figured out, but we also had Maxwell's equations for electromagnetism and light. And guess what? They did not get along. Picture two spaceships. One is moving away from Earth at, say, 5,000 kilometers per hour, and the other is flying toward Earth at that exact same speed. To someone sitting on one of those ships, the other ship is zooming toward them at 10,000 kilometers per hour, right? Speeds add up. If you throw a baseball from one ship to the other at 100 kilometers per hour, it intuitively adds up to 10,100 kilometers per hour. But if you shine a beam of light, that completely shatters this entire logic. This whole thought experiment brilliantly illustrates a paradox that absolutely tortured 19th century physicists. If you replace that thrown baseball with a beam of light, the light doesn't arrive at its normal speed plus the 10,000 kilometers per hour of the spaceship. Experimental data showed that light stubbornly refuses to adjust its speed for anyone. It totally ignores how fast the observer or the source is moving. This contradicted Newtonian physics entirely. Scientists were scratching their heads thinking, okay, light must travel through some invisible medium in space, which they called the luminiferous ether. They figured moving through this ether would change light's apparent speed depending on which way you were going. But then came a really famous test called the Michelson-Morley experiment, and it proved that whole ether idea completely wrong. They essentially spilled a beam of light, sending it in different directions relative to the Earth's motion. If that invisible ether existed, the speeds should have been different, but they weren't. Whether you are hurtling headfirst toward a light source or running away from it as fast as you can, that light always arrives at the exact same unchanging speed. The speed of light is the ultimate constant. Scientists were just baffled. I mean, how do you reconcile a universe where speeds are supposed to add up smoothly, but the speed of light simply refuses to play along? Enter Albert Einstein. Now, his radical genius wasn't trying to explain away this weird behavior with invisible ethers or complicated excuses. Instead, he did something incredibly bold. He decided to accept it as the ultimate axiom. He basically said, all right, let's just start with the principle that the speed of light is always the exact same for all observers, and we'll force the rest of the universe to adapt to that. He completely flipped the equation on its head. Instead of space and time being the fundamental constants, he made the speed of light the constant. Let's break down how this logically builds, because it's wild. If the speed of light, which is just distance divided by time, cannot ever change, then the distance and the time themselves are the things that have to change. They have to become fluid. Einstein mathematically proved that for light speed to remain perfectly balanced for absolutely everyone, time must dilate, meaning It literally slows down for fast-moving objects. And to preserve other physical laws, space itself has to contract or shrink in the direction of motion. So objects actually get physically shorter and their mass increases. Mind-blowing, right? This profoundly changed our entire concept of what space actually is. Under Einstein's view, space is definitely not just some empty, boring void. It is a highly active, dynamic entity. Remember that invisible ether everyone was frantically searching for? Einstein essentially said, hey, nothing needs to carry light. Space itself behaves like the medium. It responds to mass and energy. This flexible spacetime is the very thing that curves and warps to create gravity in his general theory of relativity. Space is no longer a passive background. It's an active participant in the universe. But wait, before we get completely comfortable in Einstein's flexible space-time wonderland, let's take a quick detour. Let's look at an older, really philosophical alternative that, believe it or not, produces the exact same mathematical results. It's a perspective that is incredibly helpful for building a real intuition about what is physically happening behind the scenes. What if the abstract concepts of space and time aren't actually what's bending at all? So, right before Einstein published his blockbuster theory, physicists like Hendrik Lorentz and George Francis Fitzgerald were pulling their hair out trying to solve the puzzle of why we couldn't detect that ether. Lorentz proposed something fascinating. He said, maybe there is an absolute frame of reference, the ether, and instead of the abstract concept of space bending, the physical objects themselves actually squeeze and distort as they move through it. Think about it. Everything is made of atoms, and atoms are held together by electromagnetic forces. So naturally, plowing through the ether subtly squishes those atoms in the direction of motion. We are looking at two radically different philosophical interpretations that describe the exact same reality. Einstein basically says the universe is relative, space and time are fluid, and the measuring stick itself defines the space. But Lorentz says the universe actually has a fixed, absolute arena, but the measuring stick physically shrinks inside it due to the harsh forces of motion, so you end up measuring the space as shorter anyway. It's wild because both ideas result in the exact same math. In fact, the equations we use in physics today are still called the Lorentz transformations. Now, Einstein's theory ultimately won out, and rightly so. It was much simpler, required way fewer assumptions, and elegantly threw out the need for some undetectable ether. But honestly, Lorentz's view is a fantastic mental tool. It really helps us grasp how deeply, physically, motion impacts matter. It reminds us that when we talk about a meter stick shrinking, it's not just some clever mathematical trick on a chalkboard. It fundamentally relates to the actual physical electromagnetic interactions holding the matter of that stick together. So if the math works perfectly, and experiments prove it literally every single day in particle accelerators, why does relativity feel so completely wrong to us? Why is it so hard to grasp? Well, if you are finding this deeply counterintuitive, take a breath. Don't worry, it absolutely should feel that way. It fundamentally clashes with the mental models our brains evolved to use. I mean, we were built to survive on the slow-moving plains of Earth, hunting and gathering. We weren't built to pilot spaceships near the speed of light. We instinctively picture Newton's abstract absolute framework because, well, at walking speed or even driving speed, that mental approximation works perfectly fine for us. We experience chemical reactions, physical interactions, everything happening at what appears to be a fixed universal rate. So our human brains just naturally invented the idea of absolute time and decided it was a fundamental truth. But here's the catch. Physical reality doesn't care about human intuition. Physics deals purely with what can be measured, and physical time, it isn't some magical flowing river. It's actually an emergent property of matter. It is defined strictly by physical timekeepers. Think about radioactive decay, the ticking of an atomic clock, or even human aging. Aging is really just a complex chemical process rooted in physical electromagnetic interactions. So, when an object moves incredibly fast, those literal physical interactions distort and slow down. Therefore, the aging process itself physically slows down. Time dilates simply because the physical processes that measure time slow down. If a concept like absolute time cannot be measured, then in the strict language of physics, it just doesn't exist. Let's imagine an alternate reality for a second. What if the speed of light was significantly slower? Let's say walking pace. If we lived our daily lives physically experiencing these relativistic effects all the time, relativity would just be our common sense, right? If cars visibly flattened out and contracted as they drove past us on the street, we would think that was completely normal. In that world, we would never ever have even invented the concept of an absolute rigid space or some universal ticking clock.
The profound takeaway here, the real mind bender, is that our intuitive picture of the world, the mental model we trust and rely on every single day, is really just an approximation of the truth. True objective reality is far more strange, deeply fluid, and wonderfully complex than our everyday human senses suggest. Relativity doesn't destroy objective reality. It just proves that reality is much, much more fascinating than Newton's simple, rigid stage. Thank you so much for joining me on this mind-expanding journey to the very edges of physics. It really makes you wonder, doesn't it? If our fundamental grasp of space and time is actually just a slow-speed illusion, what else about our everyday reality are we completely misunderstanding? This explainer was inspired by the chapter How Einstein's Theory of Relativity Redefined Space and Time from the book Simulated Reality. The book is available for free on Google Play Books. You can find the link in the description. Keep questioning everything, and I'll see you in the next explainer.